Okay, so welcome everybody to the first Do-mpc developer conference, the 2021 developer conference. So today we are going to see basically what Do-mpc is and a little bit of the history, but also a little bit of what we plan to do. And thank you very much, all of you also joining online for being here, and also those that are here. I hope this is going to be interesting for you. Both to learn what Do-mpc is, but also to maybe help you in your projects and try to have developed some features that will be useful for you. So yeah, what I wanted to show here, okay, is, yeah, that's the welcome. Yeah, that's me on the right-hand side, that's Felix on the left-hand side. So I started Do-mpc when I was, yeah, finishing my PhD more or less. Now I'm professor at the TU Dortmund. I'm heading the Laboratory of Process Automation Systems, as most of you know. Felix is a PhD student in my group. He is, since 2019, the main developer of Do-mpc. And yeah, I'm very happy that he's in charge of the project, for which Do-mpc has improved a lot in the last 3 years, as we will see later. Yeah, what are we going to do today? Yeah, we are here to introduce and demonstrate the newest version of Do-mpc, which is very different to the older versions that mostly I had been doing, and maybe some of you are still looking at or seeing, especially here in Dortmund. And maybe this helps you to know all the things that the new Do-mpc can do, and hopefully help you also in your research. Yeah, but we want to use also this to kickstart the development of new projects in Do-mpc, so new features that are very, very important, and we will see later. But for example, nowadays, well, you have a part of the model that is a neural network. Can we do this directly in Do-mpc? And the answer is yes, but it doesn't work directly in the moment. So this is what we want to do. Let's try to do it that it works very easily for everybody. Okay. And these kind of projects are the ones that we want to do. Also, we are open, of course, for your suggestions and things that are important for you. Yeah, we also want to expand and further integrate our developer base. So Have You is an open source project, so everything is open source. If you are interested, you are welcome to collaborate and really actually develop also Do-mpc. And yeah, also discuss the future of Do-mpc. If you have ideas, you think, okay, I looked at it, but it doesn't work for me because this and this, because I cannot do this and this and this, or you think, well, this feature would be very, very important, then we can discuss it together, and we can, yeah, think if this is maybe a priority for doing in the next weeks or next days. Good, so this is how it's gonna work. We are going to start with a welcome, and that's what we are doing now. We will then have the introduction to the Do-mpc features, and yeah, feature demonstration. We'll have a little bit more of time with that. Then we would discuss during half an hour what is the future roadmap, which hackathon projects are we going to use. This is the idea that especially starting this afternoon and tomorrow and the day after tomorrow, we actually do kind of a hackathon, and we actually implement things that we think are important, and we on Friday they are ready to use. Okay, or that's the ideal situation. We will then also have a little bit of explanation by Felix on what is the workflow that it is good to use with Do-mpc. So how can we use, for example, doing a fork of the repository, doing pull requests, and all these things that working with Git help us to maintain basically a coherence of the code and try to avoid introducing bugs into a code that is working. Yeah. Good. Then we will start the offline part. So until this, all our online guests are welcome to stay there. Here, since we will be discussing about programming and hackathon stuff, then we are going to do this only with the physical guests here in the offline part. Then we'll have the lunch and we'll start programming, having fun. That's it basically for today's agenda. I wanted to, show a little bit what Do-mpc was and what it is now and what it might become. Yeah. So basically, we started, or I started this during my PhD because in the framework of my PhD, I was working on a European project that was called Embocon with many other people, that many big professors on MPC in ETH Zurich, in Leuven, as Moritz Hill, for example, Morari, many others. That basically we were discussing how to deploy model predictive control also for systems that are not very, very slow and require a big computer. Yeah. And there we had designed a modular architecture that we will see that this is still visible in Do-mpc, that we have some modules like a model, like an MPC, MHE, and that you can just combine them as you want. Yeah, that was a little bit the idea. And I was sometime in Leuven with Moritz Hill working with Casadi. When Casadi was being developed, I was one of the first external users. And I basically implemented MPC, and with the scenario tree, multi-stage MPC with Casadi in a relatively modular fashion. And that was the very first version of Do-mpc. That was 2013, 2014. Then the initial commit of the repository that you can see today is actually from May 2015. Yeah, even though the original codes, they were before that. Yeah, second version that we did some modifications with, also with Alexandru. So many other people collaborated here. Yeah, so Alexandru Tetulea, also Christian Schopmeier was involved in the very first version. Yeah, Daniel Haskell also used it and did some modifications. So many different people. Yeah, okay. So then I started at 2017. I started a professorship, junior professorship at TU Berlin, and Benjamin Karg also joined 2 months after that point. And then, yeah, after some time, the third version was developed, but things changed, especially when Felix joined the team in October. Then we decided to do a retreat in Brandenburg, so in the middle of nothing, to actually do a recode of the whole, everything that we have written. We started from scratch basically, and we reprogrammed everything, okay, to make it, we had learned a little bit what is necessary to do a very general implementation of model predictive control. And basically this is what we did there. We went there 2 days and programming day and night, but having some fun also. And we basically almost did it in these 2 days, but there was some, yeah, some work to be done after that. So we did this at the end of November. In February, the fourth version, which is basically the good version that we have now, was published. And that's it basically. Since then, Felix has been maintaining and adding more and more things, but that's basically the main, yeah. I don't know why it's not going on, but yeah, okay, oops, yeah. Okay, yeah. Almost 1 year ago, on 1st of October, I moved to Dortmund, and that means that also Felix and Benjamin moved with me, for which I am very grateful, from Berlin to Dortmund. And that's it. So Lucas also, who is helping us also today, is another PhD student in our group, and who joined somewhere here in February. And yeah, that's today. So the first developer conference of Do-mpc. And I just wanted to show a little bit of what the history is to understand what Do-mpc is about, okay? But the more important thing comes now. So yeah, okay. This is the first Do-mpc retreat. So this is a little bit the spirit that we wanted to somehow recreate here. Also, yeah, nowadays a little bit more difficult with a bigger group and with the pandemic, yeah. So we had a small room here for us with monitors that we brought in our suitcases to Brandenburg, someplace in the middle of nowhere. But we had they had a bar also, so we had also time to, apart from programming, to have some fun. And this is the spirit that we would like to recreate also today to, yeah, make Do-mpc much better. Good. So maybe a little bit to show you that these ideas of this retreat, or this idea of basically starting everything from scratch, has helped. Yeah. These are the GitHub's start history. So that's basically a measure of how many people are interacting with the code. Yeah. Since I started, it was very slow because, yeah, they had many issues. The things I programmed, it was not perfect. This is the when the fourth version was, so here, approximately here is the retreat. And some months later, we have the fourth version. And then a lot of people started using it, yeah, and giving us feedback and putting stars on GitHub. You see that we have a very nice, almost exponential growth, or exponential growth, I would say, yeah. You can see also we have a web page. We have a really wonderful documentation for Do-mpc right now that you can use, and many people use at do-mpc.com. And you can see also that we have a substantial amount of visits there. So yeah, at least there are people using Do-mpc, for which we are very happy of. It's not only used in our group, let's say, yeah. Many people also posing questions, and this tells us that it's actually an interesting project to work on, and that it is worth it, the effort, and it's probably very useful for the research of many of you. And that's basically all for the welcome and the introduction. I think I did more or less on time. So the next part is going to be an introduction to Do-mpc by Felix, and we will see what Do-mpc can do and cannot do, but there is very little that Do-mpc cannot do. So we will see basically what it can be done. So Felix.
Yeah.
Thank you.
Thank you, Sergio. Thank you for the introduction, and also for giving us a perspective of where we have come from, because I feel like this is very important to understand our goals for the future. Yeah, in my part, I want to introduce to you Do-mpc, and I'm going to do this in essentially two parts. The first part is about a more of a conceptual overview of how we imagine Do-mpc, how different aspects of Do-mpc work together, basically our philosophy about the project. And then in the second part, of course, closely related to the first part, I'm going to give you a feature demonstration that should illustrate how we imagine this conceptual relationship of Do-mpc. Yeah, for the conceptual relationship, or before I go into the conceptual relationship, I want to quickly ask again the question, what is Do-mpc? And I know all of you who are here in front of me today, and I believe all of you who are in the Zoom meeting today know this question or the answer to this question, but it still helps to remember from time to time. So Do-mpc is a Python toolbox for robust optimal control, and it is based on Casadi. So it's essentially a high-level interface to Casadi that helps you configure very complicated or complex model predictive control problems, among other things. The conceptual overview of Do-mpc is given on this slide at the bottom. And one of the core elements of Do-mpc is the dynamic model. For almost everything that we do, we need a dynamic model of a system that we are dealing with, either if we're controlling it or if we want to do state estimation or whatever. We always need a dynamic model. And what we're also trying to emphasize on this slide is that you can, in general, have multiple dynamical models. So, for example, the MPC controller can have a different model than the simulator. Yeah, so this is always the first block. When you are working with Do-mpc, you need to implement your model, and we will see in a second how this works in practice. Based on this model, Do-mpc then will generally be used to initialize an MPC controller, which is this block here in the middle. And this MPC controller does what every controller does. It takes some input from some state of your system that you want to control, and it computes an optimal input to the system, which will hopefully lead to some desirable properties. And if you want to check what this input is doing without actually having the true plant in front of you, we can also use Do-mpc to simulate this system. So here on the right-hand side, we have a simulator of our system. Of course, that also needs the dynamic model, because otherwise we can't say what we want to simulate. So the simulator takes an input and returns, in the most general case, a measurement of our system. And quite often, we will also need a state estimation block, which is shown here on the left-hand side. And the state estimation block takes this measurement and computes us a state. And of course, this is also model-based, so we also need to initialize this with a model. Let's see on this slide quickly some of the features of these different blocks that Do-mpc is providing. So first of all, Do-mpc is able to deal with nonlinear ODEs or DEAEs, which means ordinary differential equation and differential algebraic equations. These models are then, for example, used in the simulator, where we use essentially an integration tool, which is based on state-of-the-art integration, for example, with CVODEs, but also other tools if you would like to do that. Then the core block of Do-mpc is, of course, the MPC block, where we are providing an implementation of multi-stage robust MPC, where if we have a continuous time system, we use orthogonal collocation to do the time discretization. And finally, for state estimation, we provide an implementation of a moving horizon estimator, which is a very, very potent estimation tool for nonlinear systems and works very well in combination with MPC. One of the core features of Do-mpc that I want to emphasize, and which Sergio also talked about, is its modularity. This is really one of our core philosophies. What we mean by this is, even though on the previous slide I showed you a complete control loop where all the building blocks that you need to run this control loop are included, you can and you should in many cases only use some of these blocks. So if you, for example, want to control a true system, you have a real plant, you will not need the simulator. This is clear, and it is very easy to do this with Do-mpc. In that case, you only use a dynamic model, you initialize your model predictive controller, and then that's essentially it. Unless you also need a state estimator, then you will probably also need that block. And similarly, if you are not interested in controlling your system, but you want to do some parameter estimation or some state estimation, just to get some additional information about your system, you will probably only need to initialize the, for example, moving horizon estimation block. And yeah, this means that our Do-mpc modules can be used in combination or they can be used independently. And this is also something we want to keep for the future, which is essential for our implementation. Finally, just a quick introduction of what you can do with Do-mpc after all this theoretical background. So here's some cool stuff, right? This is a very common example from nonlinear control. It's a double inverted pendulum on a cart. The cart is not visible, but I guess you can imagine it. It's running on this black line. And the control task here is to, first of all, erect the pendulum, which is already quite difficult. But then we also do a set point change. So we move the pendulum from the left side of the obstacle to the right side of the obstacle, clearly without touching the obstacle, which is implemented as a complex nonlinear constraint. And as we can see here, this leads to some very interesting trajectories, which are not super easy to imagine before you actually see them. And I guess this is a very nice quick introduction of what you can achieve with Do-mpc. Some further details here is we are using, in fact, economic MPC in this example, because the energy is the objective that we try to maximize, or more precisely, the potential energy is maximized and the kinetic energy is minimized in this particular example. Good. Then this brings me to the second part of the introduction to Do-mpc, which is actually our feature demonstration. And for this, I will do some live coding. So please pray with me that there are no bugs in the code. And the example that we are going to treat is a CSTR example shown here on the left-hand side. The focus of this implementation is, of course, not the example, but I quickly want to introduce it anyway so that you have a rough understanding what's going on. So it's a very simple CSTR, however, still with some strong nonlinear behavior. And essentially, the way it works is we are controlling the feed here on the left-hand side that goes into the reactor. And within the reactor, we have 4 components, CA, CB, CC, and CD. And we are mainly interested in the reaction from CA to CB. CB is the component that we want to obtain. And then there are 2 side reactions, which are undesirable but still happen. The entire reaction is exothermic, so we need to cool this CSTR. And for this purpose, we have we have a jacket around the reactor in which some coolant medium is flowing. And as a second control input, we can use a heat exchanger to remove heat from this coolant. Yeah, that's essentially it. So after this quick introduction, let's look at the code. Okay. Yeah, I believe this is large enough. Good. Yeah, I'm doing all of this in a Jupyter notebook. In general, you will probably use Do-mpc sometimes in a Jupyter notebook, but sometimes not. But for the purpose of this illustration, it helps to do it in a Jupyter notebook. Here at the beginning, I'm doing nothing particular, just importing some packages, most importantly, Do-mpc, of course. And then I'm starting with the implementation itself. The first thing, as I said before, that we always want to implement is the model, because otherwise we cannot do anything. This is a model-based toolbox. So yeah, this is what we start with. And to implement the model, we simply create a new model object, which we obtain by typing do-mpc.model.model. This is the model class, and this needs some parameters as well. Here, I want to already introduce you our contextual help in our documentation. Zoom even larger. Yes, thank you for the feedback. Like this? Good. Yeah, here I want to introduce you to some contextual feedback. So if I'm pressing, for example, Shift-Tab, I see here what I need to provide to this function call in order to make it work. So the first argument is the model type. And yeah, now you can scroll through this, but sometimes this isn't beautifully rendered. So in that case, I will like to refer you to our documentation, which I'm also going to zoom in quite a lot. And here for our documentation, for example, I'm going to the API reference, clicking on model.model. And here I see again, the input I need to give is the model type. And here at the bottom, I see that one of the parameters is the model type, which can be either discrete or continuous. So in this particular example, our model is going to be a continuous model. So this is what I'm writing here. Because I'm scared of making mistakes, I'm going to type some of the code here, but then I'm going to uncomment it and show instead the solution that I've previously prepared. Don't be surprised if I'm doing this. It just ensures that this code is actually working, because it's always easy to do small typing mistakes which completely ruin the code for you. Yeah, after I have initiated the model class, which is now an ODE or DAE, I need to define the variables to the model. And this is done by using the model.setVariable command. By the way, if you're ever confused about some of the structure, how you should set up this model, I would like to refer to you some of the examples that we are providing, and also here is some instruction on how to do this in a very general way, I would say. Yeah, model set variable, and then the first thing I want to introduce is a state. So states are called _x for us. You can of course see that in the documentation. Then the next thing I need to provide is a variable name, which is user defined. So for example, one of the states that I'm having is the concentration of component A, so CA. And then that's essentially it. And I assign this to a variable. So CA is equal to model.setVariable state with the name CA. Let's have a look at the solution that I have prepared. Yeah, so essentially the same thing. Except that I've of course introduced the other states as well. So
I'm going to do some questions. You can do some questions also, so that this is a little bit more dynamic.
Yeah.
And even though sometimes I might know the answer, but I think it might be good. So what is happening inside here when you say set variable? Yeah, are you creating some symbolic variable or?
Yes, exactly. So we are introducing new symbolic variables in the format of a Casady variable to Do-mpc. And we are storing them in a smart way so that they can get processed at some point where we are calling model.setup, which is the last step of setting up the model. So right now I'm making Do-mpc aware that in a given category, which right now is the states, I want to introduce something. So in this case, the variable CA. Does that make sense to you? Yeah.
Yes.
Perfect. Yeah. So again, uncomment and instead introduce these variables all together. Yeah, we have a question. Yeah, thank you for the question. So the question was, what is the purpose of the shape parameter, which is the third parameter here, which I have in fact omitted here. Yeah, in general, variables can be scalars, they can be vectors, and they can even be matrices. So if you are in the situation where you want to introduce a vector, for example, so I could have introduced both of the concentrations as a vector with two components. That would have been the purpose of the shape command. If I omit it, then the default value of the shape command is 1,1, which we can see, by the way, if I look here at the context help. So here, this is the default command, and this makes this a scalar. So yeah, this is the default setting. We have a scalar. And so this is, yeah, strictly speaking, it's not necessary to type this here. It doesn't change anything. Yeah, we have another question. I believe we are limited to two. So first of all, the question, are we limited to 2D arrays, or can we have multiple dimensional arrays here for the shape? So I believe we are limited to 2D arrays. Haven't tried it out, to be honest, if we can have higher dimensional arrays, but good question. Yeah. 2D. Yeah, I believe so too. Yeah, so I believe the question is 2D is the maximum. Yeah.
This can be also very useful if you are doing, for example, something with PDEs, and you can then have the discretization that you can do yourself, but then you can have there a vector of with the number of elements that you are discretizing, for example. Yeah.
Yeah. That's exactly the application, or one of the applications that we had in mind. Yeah. So I believe I have executed this code cell. By the way, notice what happens if I want to introduce another state with the same name. Do-mpc is going to throw us an error because we cannot introduce multiple states with the same name. Do-mpc is always name-based, so it's very important that names are unique. Yeah, I believe this might actually cause an... Just going to do it like this now, because this might be problematic later. Yeah, the next step is to define inputs. This is essentially the same as introducing states. The only difference is now that the variable type is input. So I'm just going to do the solution immediately. Here you see variable type input, which we denote by _u. And the inputs are the flow rate and the heat that we are removing from the heat exchanger. Here are the ODEs that we eventually want to implement. I'm not going to go into detail here. We just see that there are some strong nonlinearities. For example, here we have a state which is squared, or here we have some exponential function with a state. And also it's divided through the state. So I guess you see that this is a highly nonlinear ODE, which is typically difficult to control. But as you will see later, Do-mpc does a tremendous job at controlling this. Just wanted to point that out. Yeah, here we're just implementing some parameters, nothing super interesting. And finally, we are doing some stuff that is interesting again, which is to define uncertain parameters. So before I'm going to do this, I'm just going to give you a quick introduction why we want to do this and where this is helpful. So one of the main purposes of Do-mpc is to implement robust multi-stage MPC, which means that we are able to control systems under the effect of uncertainty. But to do this, we need to declare to Do-mpc where this uncertainty actually comes into the system. And for this purpose, we need to define those parameters that we will later treat as uncertain. And in this particular example that we're treating here, we have two uncertain parameters, which we call alpha, which is here, and here we have beta. And these parameters are, in the nominal case, just one. So they are just, one. And in the disturbed case, they are deviating from one to some extent. And to make this possible, right now we need to introduce alpha and beta. And those are essentially just variables as all the other variables that we have previously defined. So the only thing we need to change is we need to set the variable type to _p, which stands for parameter. And then this needs a name, and that's essentially it. And the same for beta. So here are these implementations, and we are done. Another interesting point that I want to talk about is the use of time-varying parameters, because they are often misunderstood, but they are quite useful for many, many cases. So yeah, we want to emphasize this in this example. Time-varying parameters are also parameters to the system itself, or as we will see in a second, also to, for example, the MPC optimization problem. The main difference from the regular parameters is that they are never uncertain. We will always know the values of these parameters, and we will also have values for the time varying parameters over the entire prediction horizon for our MPC controller. Because in general, when you're looking into the future, some parameters might change and you might even be aware of these changes. An example is if you want to control the building temperature and you have a weather forecast, then you will know with some certainty how the temperature outside is going to be over your prediction horizon. And these are going to change, and this needs to be, Do-mpc needs to be aware of these things. And for this purpose, we introduce these time varying parameters.
Could you use this also, for example, to do set point changes? Or
very good question. Yeah, exactly. This is another example where we can use them. It's a bit confusing maybe because these set point changes are not intrinsically part of the model, I would say, because it's only used for the optimization algorithm for the MPC controller. But in fact, we are also introducing these time varying parameters already in the model. And Sergio was completely unaware that we have such a case in this example. So here I'm introducing the set point for the component CB, in fact, as a time varying parameter. So this works just as expected by typing model.setVariable, and then the variable type is _tvp, and then the name is going to be cbset. Okay. But we also have a true time varying parameter, which is model intrinsic. And for this, we are going to choose the inlet temperature of the flow. So for the inlet temperature of the flow, we are also assuming that it's going to change over time, and that we might be aware of the temperature in the future because there's some upstream equipment where we can control it, for example. So this is the other time varying parameter that we are introducing. Again, because I'm scared of typos, I'm just going to uncomment this here, press show solution, and instead use this code block here. Yeah, those are my two time varying parameters now. Yeah, now comes just some computation where I'm computing the reaction rate, which is essentially just a function of some of these values that I have just introduced. So nothing crazy going on here. The next thing I want to point out, which is also super helpful, is the introduction of so-called auxiliary expressions to the model. These expressions are just functions of some of the variables that we have previously introduced, but which are neither a state nor a parameter nor anything from the various categories that we have so far discussed. It hopefully becomes a bit clearer if I'm telling you what I'm trying to implement here. So here I'm going to implement the expression, which is computing the temperature difference between two temperatures. And as we will see in a second, this is important for some of the reaction terms, or for the heat exchange terms to be precise. And if we introduce this as an auxiliary expression, we will see that we can actually see this variable later on when we investigate our solution. For example, we can see how the calculated prediction is going to look for these auxiliary variables. And this is often super helpful for debugging and for a lot of other purposes. So even though we don't necessarily need to do this, this is absolutely optional, it is often quite helpful. And
so you could define here, for example, also quantities that you are interested to plot or something like that later.
Exactly. I'm doing this quite often. You could also already introduce your cost function for the MPC controller, for example, here. And then you will see that cost function in all of the derived objects that you're creating from this model. It will not have an effect as a cost function, but you can, for example, plot it from the simulated variables, which is also very helpful in many cases. Yeah. And to introduce it, we are going to use set expression, and set expression wants an expression name. So just going to call it tdiff, and then the expression itself, which is in my case, tr minus tk. Yeah, I could also, for example, plot the values of these reaction rates, which is computed from some of the states and some of the uncertain parameters that I've previously introduced. And maybe I have been choosing, for example, like an uncertain value for one of these uncertain parameters that is unphysical or creates unphysical values for some of these derived quantities. And then I will see that later on when I'm plotting it, and it will help me a lot to fix that mistake. So yeah, I believe it is very useful to add these auxiliary expressions in many cases. Yeah, here is the same thing introduced. And then comes probably the most important step, which is to set the right-hand side of the model equation. So essentially, for all of the states that we have previously introduced, CA, CB, TR, and TK, we need to set one expression which refers to the right-hand side of the corresponding state. So for example, for CA, we see that the right-hand side is something like flow rate times this difference in the concentrations. So if I'm going here and typing model.set right-hand side, this wants first a variable name, which refers to state name. So for the state CA, and then we have to type an expression. And that expression was something like flow rate times, and then here some concentration difference, which I don't exactly remember. But I'm not going to type this anyway, because I'm just going to press show solution here. And yeah, here we see it for CA. We have, for example, this equation that we have previously seen as an equation. Just gonna execute this, and after that the model configuration is finished and we can go to the next step. But one last step is to actually call model.setup. This does not require any input from the user, but is doing some stuff in the background, which is super important.
Will I get, for example, there an error if I forgot to set the right-hand side for state?
Indeed, you will get an error if you forgot to set the right-hand side for a state. Do-mpc will make you aware which right-hand side you have forgotten. I cannot really demonstrate it now because I have forgotten none of them. Yeah. But if I were to forget one of them, the setup command does some sanity checks, this among some other sanity checks. So typically, you can expect some very verbose error messages from Do-mpc if you're doing something wrong, which at least helps us a lot to fix these errors quite easily. Yeah, this brings us to the next step, implementing the controller. As we have seen in the figure that I showed on the slides, we initialized blocks in Do-mpc by passing a dynamical model. The dynamical model is now implemented. So now we can pass this to the MPC block and configure it. And this works almost exactly as expected, I hope. So we type MPC, that's the name of our class instance, is equal to dompc.controller.mpc. And then this wants exactly that, just a model class. So we type model because that's the name of our model class that we had here, and we are able to initialize this controller. The next step is to configure some MPC settings. There are multiple settings that you can set. You don't always have to set all of them because there are default values for most of the settings. All of these settings that you can set are set by typing mpc.setParam. And here you see in the help that you can or should pass keyword arguments to this command. And the keyword arguments that you can and should pass is or can be found here in the help. So here we have setParam. And you see that there are quite a lot of parameters that you can pass. One of them is, for example, the length of the horizon, which is obviously super important for the configuration. So we're going to set that. So it just works like this. N horizon is equal to 20. And we can set other parameters, like, for example, the time step, and yeah, a lot of different things. What you will also see often in our implementations is that we are configuring some dictionary. And this dictionary can have keyword arguments and values for all of these parameters. So N horizon is equal to 20, T step is equal to 0.05. And then we just call setParam once with this dictionary, which sometimes makes the code a bit more elegant, but this is really just your preference. Note that if you want to pass a dictionary here, you need to use the splat operator, which is a double asterisk. And all this does is it unwraps this dictionary and unwraps it into keyword argument pairs, which are then passed to the function.
Now that we have been looking a lot of code, so if I'm a new user,
Yeah.
do I really need to know all this syntax by heart, or how would be the standard workflow that they would use?
Yeah, so we of course expect our new users to first thoroughly study the documentation for many, many hours, and then they can try to implement their problems. No, of course not. We have very good examples and very good templates that you can start from. And in most cases, unless you have a super uncommon problem, small changes to these templates will already be sufficient to have a first solution. And then from that, you can iterate and further improve your solution, of course. So yeah, on our documentation page, there's a lot. On our GitHub repository, there's a lot of templates and different things. Here, for example, also Jupyter notebooks of different examples that you can download and work with. And additionally, if you do in fact want to start from scratch, for example, as we have seen for the model class, there's also in the documentation quite a complex guide of what you need to do in which order to configure the model. So yeah, even I, who have programmed most of that, I forget the names of these functions, but it's really easy to find in the documentation. So yeah, I think it's quite easy to get started. Yeah, so I'm gonna get rid of this to avoid any mistakes and instead click here on show solution. And as you can see, we added some additional parameters, which I'm not gonna go into detail now, but yeah, you can see that you can change a lot if you want to. The next step of configuring the MPC controller is an optional step, but which is often quite helpful to help your MPC optimization problem for faster convergence, and that is scaling. So if you have variables, for example, states, inputs, that are operating on very, very different ranges of magnitude, then it might be complicated to solve the problem for the MPC optimizer. So in that case, it really helps to introduce scaling, and scaling is introduced in a very simple way. So you just type mpc.scaling. And if we execute this, we see that this is a so-called index property. And we can change the values of these scaling factors by passing a so-called power index. It really helps to just look at the documentation, what this function expects, but I know what it expects. So the first argument is going to be the variable type, and the second argument is the variable name. So if I'm typing this, you will see that the scaling factor for the concentration of A is currently 1, which is, of course, the default value for all of the variables that are introduced. If you want to change it, you just have to give some value here. And that's how you change the scaling. And yeah, we have a question?
Yeah, does scaling work for vector variables as well? So vector is scaled with a scalar, or are all the elements of vector scaled by?
Yeah, very good question. So the question was if we have a vector as a, for example, state, how does the scaling work? It works in both ways that you have just described. So assume that this would be a vector. If I write this here, just equal to 10, it will scale all the elements of this vector by 10. But if I write this here, it will only scale the first component of this vector by 10. So it's quite flexible in this regard, and also super easy if you don't want to think about it. Yeah, then let's just show the solution. This is the scaling factors that we introduced here. Now we come to probably the most important part of implementing MPC, the objective function, where we need to define what we actually want to achieve with our controller. In this particular example, our target is to have a certain concentration of the component B in the outlet flow. So we are going to implement a quadratic objective for the change between our current value of CB and the set point of CB. And the way this is done is quite clear to everyone who has ever worked in optimal control. It helps to have a look at the documentation for this purpose. So here set objective is what I'm looking for. Yeah, essentially what you need to implement is the Lagrange term, which is the term that is added for each step of the horizon, and the Mayer term, which is the term that is added only for the last state of the prediction horizon. And then we will see in a second that there's also another function that we need to call to penalize changes of the input. Now we want to set the Lagrange term and the Mayer term. And as I've said, these are quadratic terms, so we need to penalize the change between CB set point and CB. The way we obtain these variables is suggested to do as follows. So we write model.x, which refers to all the states of the model. And then we can again use power indexes. So model.x of CB gives me the state CB. And then model.tvp, time varying parameters of CB set, gives me the set point. And because this is a quadratic objective, I'm squaring this term now. And this is for the L term. For the M term, we are going to do exactly the same. And because I have introduced this CB set as a time varying parameter, we can change the actual value of what we want to have the set point for. We can change it later. So right now, this is still a symbolic variable. So nothing is decided what the set point is actually going to be at this point. So mpc.set objective of L term, actually, let me check, of M term and then L term. Yeah.
Could you comment on the advantages of working with time varying parameters here? Because if the set point changes, you could also just redo everything with the same problem with another set point when it changes,
yeah.
right? Like,
yeah, that would definitely work. Two advantages here. First of all, recreating the optimization problem takes its time. So we are definitely losing a significant amount of, it's going to be so much slower if we redo the optimization problem at each iteration. So this is generally not recommended to ever do. Like if you have the possibility to not redo your optimization problem, go for it. If you don't have it, maybe think about your problem for a second, because you're losing a lot of computational speed. Additionally, as we will see in a second, this allows us to also change the value of the set point over the prediction horizon. So for example, we have a prediction horizon of 20, and we already know that at step 10, the set point is going to change. This is only possible with the time varying parameters. So the suggestion of recreating the optimization problem wouldn't even work in this particular example. Yeah. And then finally, as I said before, we also want to set the penalization for changes in the input, which we call the R term. Here we are exactly penalizing quick changes in the input, which is often very good to stabilize your MPC solution. And to do this, we use the set R term method, which is here. And this method wants keyword arguments. And these keywords that we need to refer to here are the names of the inputs that we have previously introduced. Okay, so it's mpc.setRterm. And then because we have an input called f, we just write f is equal to. And then the value that we're plugging in here is the factor with which this quadratic penalty or quadratic term is multiplied and added to the cost function. So if I put a very small factor, changes in the input are hardly penalized. If I put a very large factor, the changes in the input are strongly penalized. Yeah. Again, I'm going to not use my implementation now, but the previous implementation, just to be sure. Yeah. Yeah. Question? Yes, good question. Those are the scaled values. Yeah. Good. And then next point is the constraints, which is one of the main benefits of model predictive control, that we can have constraints on our variables. We differentiate between two different kinds of constraints, which is also a legacy from Casadi and other tools that are using it in the same way. And basically we have bounds, which are just lower and upper bounds for all of our optimization variables. And then we have further nonlinear constraints, which can be any arbitrary function from states, inputs, and so on. And then we have a constraint for that. The bounds are the simpler way to deal with first. So what we need to do is essentially just write mpc.bounds. And then this is going to be an index property again, which takes 3 arguments or more if it's a vector or a matrix, for example. The first argument is if we have a lower or an upper bound. The second argument is for which type we are setting the bound. And the third argument is the name of the variable for which we are setting the bound. So here, now I have the bound for the lower bound for the state CB. And by default, there's already a value in there, which we can query. And we see that the current value of the bound is -infinity, which essentially boils down to not having a bound. So if we want to set a bound, all we need to do is just write equal to 0, for example, here. And just like what was asked before, if CB would be a vector, we could set it simultaneously for all of the elements of the vector or just for one element of the vector. Yeah, because there are quite a lot of bounds, again, just pressing show solution here. And you see that we have some lower and some upper bounds for most of the states and inputs. Then there are nonlinear constraints, for which I'm quickly going to show the documentation as well. The nonlinear constraints are implemented in a way that we pass a function, which can be a function of all of the different elements of the model. And this function must be smaller or equal than some upper bound. And this is essentially what you need to pass.
What is Z there? Sorry that I interrupt.
Z, yes. Z is the algebraic states. So if we do have this differential algebraic equation, then we refer to the algebraic states. So those that are not coming with an ODE equation, we refer to them as Z. Good question, thank you. And we need to pass this function and we need to pass the upper bound. And also we need to give an expression name to this function, which helps to find it back again later. In this example that we are treating here, we are actually not making good use of this nonlinear constraints because we're actually just plugging in a linear constraint. Just want to show how it works in practice, even though we wouldn't necessarily need it in this particular case. So yeah, I'm introducing a nonlinear constraint for TR, for the reactor temperature. And we just have an upper bound of 100 and, sorry, first I need to give the expression. So TR, and then the upper bound is going to be 140 degrees Celsius. To make it at least a bit more interesting, we are going to introduce this as a soft constraint, which is also how you would introduce soft constraints to Do-mpc. And we do this by just typing here soft constraint equal to true. That's the Boolean that we need to set. And a soft constraint essentially allows us to violate a constraint to some extent, but with a high penalty if the constraint is violated. So this is often useful if you're not able to always satisfy your constraint, because then the optimizer is still giving you a feasible solution after the constraint violation. It's going to be highly penalized to violate this constraint. How highly penalized can be also set in this function. So here's the penalty term for the constraint, which we need to set. It often takes some try and error to find good values. So here I'm just plugging something very high in. And if I want to, I could also have a maximum violation. So if I want to allow for slight violations with a high penalty, this is possible. And then there might be a hard threshold at some point. I'm not going to use that here, but it is possible.
Could you show, I'm interested in looking at how the soft constraint is actually implemented.
Yeah.
I think in the implemented. Yeah, I think in the documentation.
Absolutely. So the soft constraint, if it is activated as true, we are introducing a slack variable epsilon, which is subtracted here on the left-hand side from the function. And as you can see, because it's subtracted, this will reduce the value of this left-hand side function. So we can, by having high values of epsilon, actually ensure that this value will always be below the upper bound. And then the value of epsilon itself can never be negative, so it's always positive. And if we have an upper bound for the violation, here we have this epsilon max. And then in the cost function, we are trying to minimize this epsilon. So if the constraint by itself is already not violated, the optimal solution for epsilon is always going to be 0, because this is the lower bound and we are trying to minimize it. So that's essentially the implementation of the soft constraint. Yeah, gonna show the solution. Now we are coming to an interesting point, the implementation of the time varying parameters. So far we have introduced them in the model, we have used them in the objective, but we have not assigned any values to them. And this is the most difficult part of working with the time varying parameters, but also the most crucial part in a way. And for us, the implementation of letting your MPC optimizer know which values of these parameters to take works in two steps. The first step is to obtain a structure which is going to hold these parameters over the prediction horizon. So it's a structure that we can index and which is, in our opinion, easy to index and understand if you know what to do. And then this structure is returned with a function to the MPC optimizer, so that the MPC controller can call this function. This function changes the values in the structure, and then these values are used at each iteration step. It's going to become a bit clearer in a second when we have implemented it. So the first part, as I said, is to obtain the structure. And the structure can have an arbitrary name. So I'm just calling it like this. And we obtain it from the MPC controller by typing mpc.get tvp template. Okay, so exactly what I've typed here. And then to better understand this structure, it helps to use the .labels command, because this is going to return all the labels of the structure. We have a look at it. Here we see the first 5 labels of the structure. So there are some additional labels which I have not shown here because it's going to be too long. To understand this, we see, okay, all of these are basically power indices. And these power indices have a similar structure always. So the first argument of the power index is _tvp. That has to be there for implementational reasons, but we can basically ignore it. Then the second index is the step in the prediction horizon. So here we have 0, 0, 1, 1, 2, 2, and this goes all the way to 20 because our prediction horizon is 20. And then the third index is the name of the variables that we have introduced. So the name of the time varying parameters, okay? So remember, we said that our inlet temperature to the reactor is going to be time varying and our set point is going to be time varying. And because these are scalars, here's a 0. If those were vectors, here would be additional indexes for each of these values, okay? Yeah, and if we want to see the values of these time varying parameters as they are right now, we can use this power index notation that we basically saw here. So here's the power index. And this gives us the default values that we have set. So here we see that for the time varying parameter at time step 0 for the inlet temperature, currently we have a value of 0. And we will have the same value of 0 for all of the time steps. I can actually return it for all of the time steps. And then you can see here, it's 0 all the way down, okay? And in the same way, you can also set it. So if you want to, for example, set the inlet temperature to 130 degrees for all time steps, you can do it like this. And in fact, if you never want to change this inlet temperature, you never need to do anything again. This is just stored in the structure now. And unless you change it, it's the values that are in there, okay? So if you want to change it, sure, you can. But for this particular example, for example, we are not going to change it. So I've been lying to you all along. We're actually not going to change the inlet temperature of the reactor, but we could in theory. And that's the important part. But what we are going to change, in fact, is the set point of the component B. And for this, we are going to do the second step now of the process of setting the time varying parameters. And the second step is to define a so-called time varying parameter function, which needs to have this signature here, okay? So it needs to always take the time now as an input. I shouldn't have double clicked, and return the structure that we have just created as an output. So really all I need to do here is I need to copy the signature of this function here. And this would already be a valid time varying parameter function. It wouldn't change anything. It would just return the structure that we have here, but it would already be valid. What we want to do now is we want to do a very simple set point change. So we type if t now is smaller or equal than 0.1 hours, then the tvp struct mpc of _tvp of, for all time steps for the component cb set, or for the variable cb set, shall be 0.6. And in all other cases, so if we have, if we are after the time of 0.1 hours, this value should change to 0.5. This is not the smartest way of making use of this time varying parameters, because we are using the same value for all steps of the prediction horizon. So this maybe refers to the use case where some operator at some point does a switch and changes the set point. Okay, so we do not know in advance that there is a set point change, but we are still having that set point change. We will see later in a second, or in a second we will see how to do this in a smarter way if we already know in advance that there's going to be a set point change. But this is the simpler implementation, maybe a bit easier to understand for now. Not going to use my own implementation for safety reasons. Instead, I'm going to use what I've previously typed, and yeah, I guess you can see it's the same thing. Yeah, and all we need to do now is we need to pass this to the MPC object, which is quite easy. So mpc.set tvp function. I think I did a typo there. tvp fun, sorry. Yeah, set tvp fun. And then we need to pass this function as an argument. Okay, and again, just to emphasize this, what is happening now? We have created a function which our MPC controller is going to call at each iteration. So every time we want to get a new solution out of the MPC controller, it's going to be called. And to this function, the MPC controller is internally passing the current time. And because of this current time, this function is doing some changes to these parameters. And then with these changed parameters, the MPC controller is solving the optimization problem and returning the solution. Okay, I hope that makes sense. We will see it in a second as well.
So you could use the TVPs for anything any parameter that changes in the model. You just don't have to redo the optimization. You could just change it with a very simple function.
Absolutely, there. Absolutely. Yeah, that's exactly the purpose. And also one of the motivation of using this is that once you are in the control loop, the interface to the optimizer should be as simple as possible. We really want to boil it down of you give me an input, so you give me a state, I give you an input. And to have this very simple interface, all of these additional things that are happening in the background, like changing these parameters, is handled through this interface. Yes, another question.
Yeah. Is the TU function copied inside the controller object?
Yeah. And no, it's linked. It's linked.
It's linked, so it's possible to change the TU function outside the controller.
Yeah, we do not recommend that, but and I think there are some caveats to that, but I believe it's just linked to it, so you should be able to fix it or change it afterwards. Haven't been doing that, to be honest, but yeah, interesting thing to try out. Yeah, another question? Yes, I forgot about this. Yeah. The question was, thank you for it. The question was if we are linking the TVP fun to the MPC controller or if we are copying it. And I think we are linking it to the MPC object. So if you change it outside of the MPC object, you should be able, yeah, then it is also changed inside the MPC object, but this is not our recommended use case. Yeah, good. Then we are executing this code. So now our MPC controller knows of these time varying parameters. And the last thing we need to do is we need to set the uncertain values for the robust MPC implementation. We are not going to do robust MPC in this example. I have two more variants of this code, which we're going to go through much quicker. But in this example, we are not going to do robust MPC. So here, what we are doing is quite simple. We are just going to tell our MPC controller that the values of alpha and beta are just going to be 1. And the way we do this is by MPC set uncertainty values. I believe that's how the command looks like. Yeah, set uncertainty values. And then what this command would like to have is keyword arguments. So the keyword arguments is just going to be alpha, and the value that we are passing is 1. And beta, and the value that we are passing is 1. This has to be a list or an array, but yeah, we will see later why this is the case. Okay, so uncomment and show solution. And that's it. The MPC controller is fully configured, and all that remains to do is to call mpc.setup. So this is where the MPC controller is now creating the optimization problem in the background. So depending on what you have been configuring, this might also take a second, couple of seconds. So if you have very large problems, this is where you will wait a couple of seconds until it's finished. Yeah, now we can configure the next block, which in this particular case is the state estimation block. It's a trivial block in our example because we have state feedback. So I'm not going to go into detail about this configuration here. And we immediately go to the last block, which is the simulator, because this is a coding example. We are not having a real plant here with us today. We need a simulator, of course. And the simulator is basically just using some model and integrating this model over time. In the most general case, this could be a more complex model of the same system, of course. So a high fidelity model, for example, one that is maybe too complex to use for the MPC controller itself. In this case, we use the same model for the simulator as for the MPC controller. But again, this is why we have here multiple blocks behind each other to emphasize that it doesn't have to be the same. The simulator is configured in a very similar way as the MPC controller. So we initialize it by passing model, which we have previously configured to.
And if you could have a more detailed model, you would just have to put their model details,
yeah,
or
exactly,
whatever variable you used for the detail.
Model 02 or something.
And then you could do the MPC with the simple model and the simulation with the more complex model, which is a usual case.
Absolutely, exactly. Yeah. So yeah, in our case, we use the same model. But in the general case, you could or would use different models, of course. Yeah, then there are some parameters that we are setting. Yeah, you don't need to set all of those. All of them also have some default values, of course. Most importantly, you will need to choose the time step, which in the most general case is going to be the same as the time step for the MPC controller, but it doesn't have to be. Then the simulator also needs to be aware of how to handle the uncertain parameters and the time varying parameters that we have introduced in the model. And for the simulator, of course, the uncertain parameters are not uncertain. They are just parameters, which might change over time, of course, but they are fixed values. So we are having a slightly easier implementation here. And similarly, for the time varying parameters, we don't need to provide a trajectory of future values of these time varying parameters because the simulator only simulates a single step. So all we need to do is essentially pass one value of the time varying parameters and one value of the parameters. And yeah, that makes it a bit easier. But the concept is very similar. We need to get a TVP struct for the simulator, which we get by typing simulator dot get TVP template, and the same for the parameters. Not going to do this here. Instead, I'm pressing show solution. So yeah, here we're getting these two structures for the P and the TVP variables. And then we need to define the analogous functions for the time varying parameters and for the parameters. And yeah, essentially it works the same as what we have just discussed before. So for example, let's say for the P struct simulator, for the value alpha, we are just going to set 1 and we're never going to change it. Same for beta, which I'm not going to type now. And for the time varying parameter struct, we need to set the inlet temperature. And this should be the same as what we set for the MPC controller because we're actually not doing any kind of like uncertainty affected system here. So now these structures are set and we can really implement the most basic time varying parameter function, which essentially do nothing but return these structures. They're not going to change anything. Okay. So I've already implemented this. Here it is. So we set the values to the time varying parameter structure and to the parameter structure. And then the functions that we have introduced here only return the structure without ever touching it again. So it's quite trivial, but it allows for a lot of flexibility if you are in the situation where you need to change these values dynamically. And then finally, we just set them to the simulator, quite easy, like this. And the last thing to do is to call simulator.setup, and we are done with the simulator. We have a question, yeah?
Why did you not have to set the value for C step?
Yeah, very good question. So the question was, why did I not change the value for CB set, which is also a time varying parameter, which is, yeah, absolutely true. The answer to that is that it already has a default value. When we created this TVP struct by calling here simulator.getTVP template, we are setting default values for all of these time varying parameters. It's always going to be 0, okay? And because the set point of the concentration of component B is not affecting the model itself, it's only affecting the controller, we can absolutely neglect it. It's having no influence whatsoever on the integration of the model.
So the purpose of the simulator is basically we don't have the real parts, we just simulate the part.
Yeah.
So my question is, could we use some other software to simulate it, for example, like Aspen, for example, because sometimes things can become really complex. And,
yeah. So let me repeat the question. The question was, the purpose of the simulator is to simulate the true plant, which is correct. And then the question was, could we use some other software to simulate the plant if we don't have a real plant, like Aspen, for example? And the answer is yes. So Do-mpc returns you some input in Python. And there are multiple ways to get this into another software. I don't know exactly how you would interface it with Aspen, but for example, one of the projects that we are working on today or during the next 2 days is to improve our OPC implementation. So I'm not sure if Aspen can actually access OPC data from an OPC server, for example, or if there's any kind of interface between Aspen and Python. There are also, of course, hacky ways to transfer this. So maybe Aspen isn't like the best example where it's super easy, but what always works, for example, is if you are able to export an FMU from whatever kind of software and use PyFMU. And this can be used and has been used in the past to simulate this complex model wherever it comes from within Python, where at each time step of the simulation, you pass one input from the MPC controller. Yeah, but yeah, very good question. Okay, yeah, then we continue with the last part of this notebook, which is the closed loop simulation. So now we want to run these 3 blocks here in a loop. So we want to have the MPC controller compute an input. We want the simulator to simulate the plant for this input. And then we want our trivial state estimation block to get back the state for the controller to repeat the cycle. And to do this, the first thing I always like to do is to set the initial condition for all of the blocks. Here we're going to do a trivial example where all of the blocks have the same initial condition for the states. Of course, in the general case, you might want to have a different initial state for the simulator and for the estimator, for example, and hope that your estimator recovers the true state of the system. But yeah, you will see how this works, but we are not doing it here. So the way it works is you type mpc.x0. And this is, again, something that you can index. So here you just type the name of the variable you want to set the initial state for. So for example, CA. And we can see what the current initial state is. It's just 0. So now I could set some value here. I forgot what the true value is. I will just look at the solution in a second. And we could do this for all of the states of the MPC controller. And if we are super lazy, we are then typing x0 is equal to mpc.x0 to recover that initial state, which is now fully set. And then we are just setting the initial state for all of the other blocks like this, okay? So this is one of the preferred ways of setting the initial state.
But you could use there just any different initial state for
Yes,
any of the
absolutely.
models.
So now, for example, for the simulator, I could have CA is equal to 0.6, for example. This definitely works. And I mean, in many tests, you should also do that, of course, to have a more realistic implementation or implement a realistic test. Yeah, let's have a look at the solution. So essentially what I've been doing, just with some different values. The only thing that I have not been talking about is this mpc.setInitialGuess. This is essentially just taking what you pass to the MPC controller as the initial values and assumes that these values are going to be the same for all of the steps in the prediction horizon. So we are setting the initial guess for the optimizer. It's often recommended to set some initial guess which is not all zeros, because, for example, in our example here, we would actually have a failure if our initial guess would be all zero for all of the states, because if you look again at the ODEs, you see here that actually it wouldn't be a problem, but here we are dividing by one of the states. So if there wouldn't be like an additive term here, having an initial value of 0 would result in, nonce essentially. So the optimizer couldn't find a solution. So always use this set initial guess method. It really helps a lot. Yeah, so let's execute this. Yeah, question? Do you mean to a more complex thing than just using the same values for all the steps of the horizon? You can, in fact. The initial guess is stored in a property which is called opt_x_num, which is, I would say, a more advanced way of using Do-mpc. So you could directly interface this and change for each time step, for each scenario, and for each collocation point, and for each of the different states, you could choose a value. If you have some very elaborate initial guess, that is absolutely possible. But generally speaking, it's already good enough, or in many cases, it's good enough to not have all zeros for the initial guess.
This is also the initial guess for the very first optimization. We are, of course, using, if we are using MPC, the initial guess in the next steps is not maintained constant like this one, but it's chosen in a more reasonable way.
Yeah, absolutely. Our MPC controller is, of course, warm starting. So we're using the previous solution as a warm start for the next solution. And we will see in this example, I don't think we see it, but for example, for the double inverted pendulum, we see that the first step takes significantly more time than the second step. And from there on, it's a super fast optimization problem. Yeah.
But it is true that if you do have a good initial guess, the very first optimization might be problematic if you have a very complex problem. Yeah.
Absolutely.
So if you have something, it is good to put it there.
Yeah, we have another question.
How do you initialize the
How I initialize?
when you're running the MPC, how do you fix the next step so there's one additional point you take that
Do you mean, maybe it becomes clear when I'm showing the main loop in a second.
No, but he means for the initial guess in the next step.
If
you really take the shifted solution, there is one step that you don't have the solution. So how do you deal with this problem, or do you? Yeah,
we do Sergio repeated the question. We do the naive approach. We just use exactly the same solution. We see that this seems a bit illogical, but in practice it works surprisingly good. It returns very, very good results. It certainly accelerates the process a lot. We have tested at some point shifting to, and maybe like keeping a constant value at the step n+1 or something. It doesn't help a lot. So yeah, we are just using the naive approach.
I think sometimes what you win with having the shifted solution, you lose it because you are choosing a bad last point, and then at least you know that the previous one that you solved, it was feasible. Yeah. So.
Yeah, that's good. That's exactly true. Yeah, and then the next point is to actually run the main loop. So now we have set the initial state for this main loop. Now we need to run it. This is quite simple. It's just a loop. So it works like this. We have a loop over some number of simulation steps, here in my case 50. And in this loop, all we are doing is we are first computing an input to our system with the mpc.makeStep command, which takes the initial or the current state of the system. Then we are computing the next measurement of the system with the simulator.makeStep command, which takes the input. And then finally, we are obtaining the state again, which takes the which is computed with the estimator.makeStep command, which takes the current measurement. Again, in this particular example, the estimator doesn't really do anything. It's just forwarding whatever we got as a measurement here. But in the general case, this is how the loop looks like, and if the estimator actually does something of importance.
And you can see here the picture that Felix was seeing. This is the beauty of the, once you have done all the definitions, that's the 3 blocks you have, and you just have to somehow iterate between them.
Yeah, yeah.
And
exactly.
if you would like to have some parallel simulations of other models for monitoring, you could just simulate at the same time 3 different models of different accuracies and do comparisons about the states. So that's basically the idea of modularity that you see there.
Yeah. Yeah, absolutely. So let's run the loop and hope I didn't forget any of the code blocks. Looks good. So here we get the output from the optimizer, which is, by the way, IP-opt, as we have configured it at the moment. Also running with solver M827, which is a linear solver, which accelerates the solution time quite a bit. So I can really recommend that. And we see that we have some 64 milliseconds to solve the problem in the first step, and then it reduces quite significantly in the second step, which is most likely because of the better initial guess. Yeah, this is essentially the solution. We have now solved our problem or simulated it for 50 steps, but of course we want to understand what has happened now.
And just to mention again, Felix mentioned it also, Casadi is used basically everywhere. Yeah, so
yes.
It's powering all Do-mpc, and it's computing automatically first and second order derivatives for IP-opt.
Exactly, exactly. That always needs to be emphasized, of course. Yeah, and then we want to have a look at the results. A great way to fix or to have a first impression on your results is to use this default plot, which gives you with integrated labels, depending on how you have called your states and inputs and so on, gives you all of the the information that you have won by running the MPC loop. So here, for example, what we can see in this plot is that for the concentration of component B that we are actually interested in, we have first a set point of 0.6, which is met quite nicely. And then after time 0.1 hours, we change to the new set point of 0.5. So from this first impression, we can already tell that the control task was probably successful, but we can do even more. And one thing that is really nice to do is to, do a more customized plot. And for this customized plot, we initialize a so-called MPC graphics object, which is done here. And then with this MPC graphics object, we can do a lot of things. The most basic thing that we always want to do is we use the MPC graphics.addLine command, which, if we look at the documentation, doesn't show me anything. Maybe I misspelled it. Let's have a look. Yeah, should be correct. So what we need to do here is we need to give as the first argument a variable type, then a variable name, and then an axis on which to display this. And here, for example, I want to display a state, which is CA on the axis 0. And why I'm doing this is because I want to have a plot in which both CA and CB, so both concentrations, are on the same axis, to have a more compact representation of this data here. So now I do the same at line for CB and for the same axis, of course. Yeah, and this I do for all of the lines that I'm interested in. So if I press on show solution, I have done this for everything that I've been interested in. For example, I've also put the set point in the same plot as both of the concentrations, and I have put both temperatures in the same plot. And then you can do what you're used to doing. So I've been setting custom labels, I've been setting some custom legends, and so on and so on. And if I execute this, I get this. Oh, my apologies. This should have been in here. So if I'm executing this now, I'm getting this nice plot. And you can essentially see the same thing as before, but maybe in a slightly more compact way, which could already be used for publication potentially. And what we also like to show to you is that you can do some interactivity quite easily, which might help you a lot to understand your solution. Okay. And here, for example, I've been using some IPython widgets or Jupyter Notebook widgets where I am, let me just execute this, then you should see it much better, where I'm introducing a slider, and I can slide over all of the time steps of my prediction horizon. And now, if I'm sliding here, I see what my MPC controller is seeing at each of these time steps. So this is this dashed line here. This is the prediction of my MPC controller, and then the solid line is the actual performance of my system. And what I want to emphasize here is, for example, the use of the time-varying parameters, because we have implemented them in such a way that they are always constant, so always 0.6. Even here in the prediction beyond this point 0.1, we are changing the time-varying parameter for the set point. But we are changing them in a maybe not super smart way, because sorry that I have to zoom out just once more, but it makes it easier to see. So if I'm going here to the point 0.1, you see that, zack, the set point has changed to the new value. And now the set point is overall always at 0.5 for the component CB.
But your prediction was not taking that change into account.
Absolutely not.
This my model also a real solution, a realistic situation where you don't have the information that a change is going to happen.
Yeah.
But sometimes you do have this information.
Absolutely. Yeah. Here we are kind of mimicking the scenario where the operator walks into the room and decides to change the set point. And nobody knew this in advance, and then it's just happening. But of course, in many cases, you will know it, and then we can also take this into consideration. And this is, in fact, what I want to show you next. So yeah, we are done with this example. So in this very next example, which is much faster to show to you, it's essentially the same code. The only difference is now that for the time-varying parameters of the controller, we are considering the fact that we will know in advance when the set point is changing, okay? And yeah, there are multiple ways of implementing this. I'm showing you here one implementation where the time-varying parameter function that I'm now creating actually uses this input tnow. And from this input tnow, it's computing a switching index. So it basically denotes the step of the prediction horizon where the switch is going to happen. And of course, the switching index moves closer to you as you go forward in time, which hopefully makes sense. And then until the switching index, we are going to have the set point 0.6. And after the switching index, we're going to have the set point 0.5. So this is how we actually intend to use this TVP fun, to actually change the values of the time varying parameters over the prediction horizon. And let me just fully execute this code, and then we can see what this has changed for us. Shouldn't take too long. Yeah. Here we have the animation again. Yeah, we can already see the change. Already at the first time step, we see that at the end of the first time step, we are going to change the set point. And as I move forward the slider, you see that this change is moving further towards us. And as a consequence of knowing this change, we have a much better transition from one set point to the other. I hope I still have the figure online here. Yeah, here we see that because we did not know of the set point change in advance, it actually takes quite a bit of time after the set point change where which we need to actually do the set point change. But if we know this in advance, we have this much better transition from one set point to the other. And we actually have this anticipating behavior that we actually like to see with model predictive control. Yeah, very nice. Now two tiny examples regarding robust model predictive control, because this is a toolbox for robust model predictive control. And in the first example, I want to show you what happens if you actually do have uncertainty in your system, but you do not consider it, okay? So we are still having a non-robust controller, but we do have an uncertain system. And yeah, I want to show you how this uncertain system is being implemented. So everything is just as it has been before, except for in the simulator, we now need to change the values of these previously introduced uncertain parameters. So in all the examples that we had before, alpha and beta were always 1. So they were just the same as we had in the MPC controller. Now we set a TVP function, which I'm showing here, where the values of alpha and beta are randomly chosen at each call of this function. They are randomly chosen between an upper bound and a lower bound. So the lower bound is here 0.95 for alpha, and the upper bound is 1.05 for alpha, and then for beta it's 0.9 to 1.1. Okay, so these values are now randomly chosen at each iteration, and we are still not considering this in the MPC controller. Now I want to show you what happens in this scenario. Yeah, we see that our controller predicts that things are looking very nicely for us. We are slowly going towards the set point, and to do so, we are actually approaching with the reactor temperature this constraint here, which is this red dashed line. Okay, and as we go forward in time, things are not as smoothly as expected, because you can see this wiggly behavior, which comes from the fact that the parameters are slightly different from what we have expected. We still predict to be very close to the set point, sorry, to the constraint here. But as we go forward in time, oops, that was a bit too far, we will see here that something unpredictable happens, because one step further into the future, we have actually violated this constraint because the parameters were not as expected. This violation is not a major issue, because if you remember correctly, we have implemented this constraint as a soft constraint. Where is it? Oops, too far. There, yeah, here. We have implemented this constraint of the reactor temperature as a soft constraint with a high penalty term, right? So we can, in fact, violate this constraint. But what happens if we violate this constraint is that our controller now experiences this very high penalty, and therefore does everything to go below the constraint again. And this actually impacts our control performance. We actually now focus on not violating the constraint anymore, and actually deviate from the set point that we wanted to reach. Now we see this here if I go a few steps further. So yeah, we have, first of all, here this high peak, both in the states and also in the inputs, to reduce the temperature. And as a consequence, we are both predicting and realizing a trajectory for our CB component, which is far off from our set point. So yeah, this is really not perfect behavior, and it hopefully illustrates the fact that we need to do something to fix this problem with robustness. And this is then the next step. So what can we do to fix this problem with robustness? And that is robust multi-stage MPC. So again, the same implementation as before. The only thing that is different now is the following. We have initialized or set up our MPC controller with the setting n-robust is equal to 1. Previously, we have not chosen n-robust, which means the default value of 0 was chosen. And the second thing that we are changing now, just zooming in while I'm looking at the code, is that we need to let our MPC controller know of some of the scenarios of the uncertainty values. Yes, Benjamin?
Why do we have this n-robust? Why do we have different values? What does it mean?
Yeah, let me quickly introduce the concept of the certain uncertainty values, and then hopefully it becomes a bit clearer, okay? So first of all, what we need to do now in this multi-stage robust MPC approach is we need to define scenarios. Scenarios, what could happen in the future. And the way these scenarios are defined is by giving our MPC controller variants of the parameter that is uncertain. So here, these variants are for alpha, for example, 1.05 and 0.95. And for beta, it's 1, 1.1, and 0.9. And essentially, the MPC controller is now doing all different combinations of these uncertain parameters. So it's considering what happens if we have alpha equal to 1 and beta equal to 1, alpha equal to 1.1, beta equal to, and so on. Like all the different combinations are now considered, which means that if we have 2 parameters, 3 realizations, this gives us 9 different combinations, okay? And these 9 different combinations are now considered at each step of the robust horizon. So since our robust horizon is 1, we are considering at the very first step 9 different scenarios. If the robust horizon would be 2, for example, we would now at each of these 9 different scenarios again consider 9 different scenarios, which would already increase the number of scenarios quite dramatically.
Maybe we could show a picture of
Yes.
the scenario 3.
Yes, I think that helps a lot. Notice that we also have some background information on topics on our Do-mpc website. So here on the basics of model predictive control, we are showing how to use robust multi-stage NMPC. And here we have this very nice figure. So in this case, we only have 3 different combinations of uncertain parameters. So in this plot, we have 9 here in our example. And what is happening now for the initial state x0, we are considering what is happening for each of the different scenarios. And then for each of these scenarios, we are again considering potentially what is happening if we choose the different scenarios. And this is the effect of the robust horizon. So we have robust horizon 1, so we do not branch out again after 1 step. Here in this plot, we have a robust horizon 2, so we branch twice. And of course, you see that the more you branch, the more complex the tree becomes. So there's some certain compromise between how far you should branch. This often involves a bit of trial and error, unless you want to do it very rigorously, of course. As we will see in a second, it helps a lot with the robustness.
Yeah. And if you choose the robust horizon equal to 0, then you would have only one scenario, which would be the standard nominal case.
Yes. And before I answer your question, one more thing important about this approach is that for each of these scenarios, we are then computing an independent input to the system. And this is what makes this, this approach also a closed loop robust MPC approach, because it allows us to consider that if we land at this point, we are going to use a different input in the future than what happens if we land at this point. And because of this, we are much less conservative in what we are doing to ensure our robustness. Then there was a question.
More like an advanced question. Considering that we start with the states and we are just expecting that the upper values are more, is possible to wait the tree positioning? That's, I mean, maybe not in Do-mpc, but in general.
I mean,
for example, sometimes it doesn't matter if the state goes down, right? But really the big problem only is if it touches the constraint. So
yeah.
is there a way to basically wait somehow?
So the question was if there's a way to weight these different scenarios with respect to constraint violations. For example, if an upper bound is more problematic than a lower bound. So for this purpose, you don't need weighting because, of course, the constraints are satisfied for all of the scenarios. And if your upper bound is more important than the lower bound, maybe you don't even have a lower bound, right? So in that case, yeah, all of them have to consider the upper bound, and maybe the lower bound is very low, so it doesn't really matter in that example. And then, of course, only the upper bound is going to make an impact on your solution. The other question is weighting with respect to the cost function. So in the cost function, of course, we are also considering all the different scenarios, and there it would make sense to some extent to weight the different scenarios, because maybe one scenario is much more likely than another scenario. And this is currently not implemented, but this is certainly something that is supposed to come. But yeah, waiting for the constraints is not necessary. All of the constraints are satisfied for all of the scenarios. And yeah, that's the nature of the constraints. They are either satisfied or not. No waiting is possible in this respect.
But waiting for the cost is something that, I mean, at least in the theoretical framework, it is possible and it is done. Yeah, it should map your knowledge about what is expected.
Yeah.
And then the expected value that you get out of that controller that is correctly weighted should be better than if you weight with the same weights or if you weight it in a different way. Yeah. So, but this is only going to affect performance, yeah, not constraint violation.
Yeah.
And this is a reasonable thing to do. Maybe it's something one can add also to Do-mpc to do it. Yeah.
Yeah.
It's yeah.
Very, very true. Yeah. And yeah, what we have now done essentially here is we have defined these scenarios. So the scenario is always defined by one combination of all of the uncertain parameters. We have now defined 9 different scenarios by having these 2 uncertain parameters. Yes.
So just one last question. Considering the scenario
U0, 1, 3, 2 would be actually the same?
Yes, yes, and exactly. They are going to be the same. Yeah, because at this point you don't know your uncertainty yet. You are applying some input to the system, and then depending what kind of uncertainty is going to be realized, this is going to affect what is the outcome. But the input is going to be the same for all three different scenarios here in the beginning. So this U01, U02, and U03 are the same, which, by the way, was the question which I forgot to repeat at this point. Yeah. Exactly. The same holds for the second stage. So here, these three inputs are the same. These three inputs are the same, and these three are also the same. Because, again, we don't know yet which of the uncertainties is going to be realized.
If you are interested in more details about multi-states and MPC, there are a lot of papers there that you can also have a look, or contact us, and we will be happy also to
Yes, definitely. Yeah. Yeah, so now we have set these values, and we need to use the robust multi-stage MPC controller. We don't need to change anything at this point. We have set up everything that we need to do. So let me just run this code. The only problem with robust multi-stage and MPC is, of course, that it is slightly slower than the previous implementations because we have so many more optimization variables. But especially for this example, it's still reasonably fast, much, much faster, in fact, than the sampling time of the system. And yeah, here we go. We have the results already. And you notice that things look a lot differently than before. Because now in the prediction, we are not showing one prediction line, we are showing multiples. In fact, we are showing 9 here because we have 9 scenarios. And this is the first visible difference between the previous implementation and this implementation. And you will see that this tree of different scenarios is going to be always there at each of the steps. It's just going to change depending on what has happened. But now it is, for us, it is now interesting to see what the effect of this robust approach is. And I think we see it most clearly in the trajectory of TK, of the reactor temperature. This was the one that was previously problematic. We were very close to the constraint, and occasionally there would be some parameter that would drive us beyond the constraint. We would violate the constraint. But now, because we are expecting that there could be some parameter realization that would drive us much closer to the constraint than what we anticipate in most of the other scenarios, we are actually staying far off from the constraint. So there's some sort of safety margin that is now implicitly calculated. We never told the MPC controller to do the safety margin. It's just a consequence from the fact that some of the trajectories are predicted to go much closer to the constraint than some of the other.
And this word implicitly, it's very important because you can always tell a controller, okay, just stay a little bit farther away, but how much is something very difficult to know in advance. Yeah. And just by having the scenarios, you are basically computing this implicitly in a simple manner.
Yeah, exactly. And as we will see as I'm scrolling forward, this computed offset from the constraint is sufficient at all times to not violate this constraint. So we are having a much better performance. Now comes the set point change. So yeah, we are changing our behavior, but this has nothing to do with the robustness. And again, after the set point change, we are staying off of this constraint, and we see some of the scenarios actually predict that we would go very close to the constraint. And because of these scenarios, we are again keeping our safety distance from this constraint. Yeah, and because there's no lower bound here anywhere close, of course, we are completely ignoring the lower bound. So all of the emphasis is now put on this upper bound, which is here the most critical one to satisfy.
And this is a very nice or unique feature of Do-mpc is that for any MPC that you implement, you can do robust NMPC, multi-stage NMPC, which is a difficult thing to implement, pretty difficult. You can do it just by changing one number, basically. Yeah, put a robust horizon equal to 1, and you have at least a try to robust NMPC.
Absolutely, absolutely, yeah. Yeah, then this is it. The feature demonstration is over. Are there any final questions regarding the feature demonstration? Benjamin, could you monitor the chat for me for a second? Is there anything? Any further questions from the audience? Yes.
How does the normal or the default plot like when you have different variables such a vector together, or do you get like for each?
Yeah, if you have a vector with multiple components, the default plot plots them all in the same subplot,
Okay.
which is often quite useful. Yeah, but in general, I mean, the default plot for us is really meant to. Oh, I moved something. Is meant to get a first impression of the results. So, yeah, if you don't like the representation of the default plot, just go for the custom plot. But yeah, the idea of the default plot is if you have a vector, it's plotting all of the elements of the vector into the same subplot. Yeah. I again forgot to repeat the question, but I think it became quite obvious from my answer. Okay.
Maybe we can have a look at the agenda.
One
we
second.
have more questions, sorry.
Yes. Different models for different scenarios? No, not natively. You can, of course, kind of fake it by implementing your scenarios as some sort of binary on-off thingy, and then in one scenario you are multiplying the right-hand side of model 1 with 1 and the right-hand side of model 2, 3, 4, 5 with zeros. So in a slightly hacky way, I would say it works. Maybe it's not even that hacky.
This could work. It's not hacky. I mean, I don't think you can just have your right-hand side as the sum of two models.
Yeah.
And your uncertain parameter would be an alpha 1, alpha 2 that multiply those two models. And the possible values of alpha 1 could be, one should be either 1 and 0, and the other should be 0 when the other is 1. And so, yeah, so you would have 1 minus alpha 1, something like that. So in that way, you could implement it directly without doing anything else, using exactly the same implementation as here.
Yeah. Filippo? Yeah, so we have a comment from the audience that in this approach where we have the sum of multiple models multiplied with some uncertain parameters, this could lead to some numerical problems if one of the models is not valid in a certain region, which I mean is a very specific case, to be honest, but I guess it could happen. And the suggestion from the audience is to use the Casadi if-else command, which could be triggered with, again, one of the uncertain parameters, I believe then. So yeah, I mean, there are multiple ways, is I guess the takeaway here to do it. And depending on your specific problem, summing multiple models might not work. I believe in many cases it will work just fine.
Even if the model is unstable, then non-stabilizing control is applied to that, then the model will just go to infinity and then
yeah, but since it's always multiplied by 0, yeah, so I do think that multiplication will not be even done because Casadi will know that that part is 0.
Yeah, I believe so too. So again, the comment was that if we have an unstable model in one of the submodels, that would go to infinity if we are not using a stabilizing controller for that submodel. But yeah, I think, as you said,
but
if we
multiply
the right-hand side,
have to look at it in detail.
Yeah, I'm pretty sure maybe there is a scenario where this doesn't work, but I don't see a general problem, to be honest. Good. Yes. Parallelization? Not really. So if you use IP-op with some advanced linear solver. This linear solver, if you have compiled it correctly, is going to use some sort of parallelization, but in general, you cannot easily distribute this among multiple CPUs or even multiple computers. Yeah. Yeah, the question was, again, I'm always forgetting, the question was if we can use parallelization, but I believe this also became clear from my answer. Yeah, good. Thank you so much for your questions. Then I would say we have a short look at the agenda. And it is now, yeah, much later than we anticipated because of technical issues and also a longer presentation than we anticipated. Thanks to your questions, but yeah, no complaints on that side. We have a last part, which is about the collaborative work in Git. Maybe we do a very short break of 5 minutes and we do this last part then, and we skip the, we have this part now. Yeah, sorry. This part we should still do now, I think.
We can do this.
The project and future roadmap. Yeah. Okay. Yeah. Okay. So we do the next part still, and then we see if we do a short break. Maybe it's time for lunch, and we stream the second part later or something.
Yeah.
Yeah, makes sense. Good. Then
I will do this very fast.
Yes.
I can do this very fast.
So yeah, thank you, Sergio. Should I go to the right slide?
Whatever you, yeah, if you want.
Here we go.
You want to go?
No, I just want to. Can you stand here, Sergio, because you're moving out of the frame otherwise?
Yeah. Oops. Sorry. Yeah. What's our mission? What do we want to do with Do-mpc? Yeah, we would like to make Do-mpc a universal platform for research and development for optimal control, where you can really do almost anything in a very simple fashion. Yeah, if you have a complex problem, you can use Do-mpc to solve it. You have a complex problem, you have to deploy your controller on an industrial computer, you can use Do-mpc to do it. Yeah, you have a complex IT infrastructure that uses OPC UA to exchange information between sensors, different computers. You can just use Do-mpc to do it. Okay, that would be the big thing that we would like to do. To achieve this stage, which is still not there, but it is going in a good direction, there are some things that need to be done. Yeah, and we thought that those might be some of the plans for the future, and some of the things that we can actually do during this first Do-mpc developer conference / hackathon. Yeah. And we had defined then together different possible projects that we think they need to be done. And this is what we, or some of the parts that we are going to work on in the next stage. We are also open for things that you think are important and should be also incorporated, that because whatever they are very important or they are important for you, they do not have to be exactly the same set of projects. And but at least those that are listed here, we do think they are important. The first one will be neural network support. So a lot of you maybe, or we are working a lot with neural networks in different fashions. A possible thing is, well, your model is a neural network, your dynamic model is a neural network because you have collected a lot of data, or you have used AspenTech to simulate data, and then you feed a neural network to this model, then your model is now a neural network. Can you use this directly into Do-mpc? Yeah. So we have actually done this already many times, but there is still not a standard way to do it automatically. And this is basically what we want to do. Yeah. Basically being able to have neural networks that describe a dynamic model, and just as simple as we had seen before, with a line of code, incorporate this model into Do-mpc and use this model to make predictions and compute optimal control inputs. The idea is basically we want to keep on using Casadi because we like it a lot. And these trained neural networks that you have trained using your preferred framework, whether it's TensorFlow, PyTorch, whatever you like to use for machine learning, then they are automatically transformed. Yeah. We would like to try to use some standard for ONXX for Open Neural Network Exchange, so that no matter what you are using, whether it's Keras, TensorFlow, all these, they can export into a standard language, and we can then use this standard language to incorporate in Casadi. So no matter what's your preferred machine learning tool, you can actually use Do-mpc for it. Okay. Good. So that would be the idea of project 1. Project 2 is related to it, in which it is also using ideas of machine learning, but here project 2 is based on the research that, together with Benjamin Karg, we have been doing in the last 3 years. 4 years almost, 4 years. No, 3 years, well, 4 years. Yeah, I think it was 4 years. In which we try to, if we want to implement MPC in real time, for some examples, either we don't have the hardware necessary to install all these solvers and run this Python and IPOpt in our computer because it's a simple PLC or a simple industrial computer, or it's just very fast. Yeah, and if we have very complex MPC controller with a lot of scenarios, it might take some seconds, or maybe 10 seconds, or maybe 1 minute to compute. But our problem is very fast. Yeah. So what do we do? Yeah. And there is one thing we can do. We can solve a lot of these problems offline, sample in an intelligent way, and approximate the solution. So given a system state or some measurements, give me the optimal control. That's what MPC is doing all the time. Okay, so it's doing this mapping. We do this mapping implicitly by solving the MPC problem, but it is just a mapping. Yeah, it is a function, but it's a very complex one. So what we can do is we can sample a lot of these values and try to learn this function using machine learning tools, which are known to be good function approximators. Yeah, that's basically what we have done, and this is what we call here learning-based MPC. We have done this already for many, many different examples, even for multi-stage MPC. We have implemented this on real examples, on microcontrollers, on FPGAs, on GPUs. So you can, once you learn it, you have a neural network that is approximating your MPC controller. And it is extremely easy to put in any place, because a neural network, when you have trained it, is just a matrix vector multiplication and some very simple function evaluation. Yeah. So you can put it everywhere. Yeah. So we are doing this, for example, also to do MPC on power electronics, on things that have to go at megahertz. Yeah. So you can do this also with that. Good. So this is, of course, going to have some synergies to the previous support, because we are going to use this standardized interface for neural networks. Yeah. And the idea here is that you design your MPC controller, as Felix has done. You click write one more line and say, okay, learn the controller using neural networks, and automatically there will be some sampling happening and a lot of optimization problems. You will learn automatically the network. In an ideal world, you will have a network just mimicking whatever your MPC controller was doing. Okay, that's basically the goal. Yeah, of course, there are many steps in the middle. We can do some of them. There are some essential control features also that are missing and that might be also important. For example, we could have automatic linearization of your models because this is very, very easy to implement with Casadi and with the tools that we already have. Yeah. We could have also some standard controllers and estimators, some more. Yeah. Instead of having MPC, we could have LQR, for example, just to have some benchmarks, some simple controllers to which we can compare. We could have extended Kalman filter, which is very easy to implement, but it is still not been done in Do-mpc. Yeah. We have done it in some cases, but there is still no general implementation of Kalman filter that works for any model. Yeah. But with the concept that we have now, with all the data structures, that should be also very simple to do. Yeah, and the idea of this, or our motivation to do this, is because, yeah, those are usually important references to compare if you are doing MPC or you are doing some fancy estimator, you want to compare with something, and if you have it already here ready, then it's going to be very easy to get your results. And also they can be used for data generations for some of the projects that we have done before, where you need to generate some data. Another project that we are working a lot on, also motivated by our research, is NLP sensitivity. So you can compute the derivatives of optimization problems, to some parameters. So if I change some parameter of my optimization problem, how is the optimal solution going to change? Yeah, that's what it's called usually in this concept, NLP sensitivity. NLP means here nonlinear program. Yeah, if you have an optimization problem, nonlinear non-convex one with some parameters, you have some optimal solution of it. Now, if some of these parameters change, how is the optimal solution going to change? That's what NLP sensitivity is. And we are going to implement different ways to compute these sensitivities efficiently, because this is going to help us in a lot of different applications. We are not going to go into the details, but basically you can speed up a lot the computation of NLPC using these sensitivities to compute a very good initial guess. That's more or less simplified is what advanced step NLPC is. You can use these things to do automatic tuning in moving horizon estimation of the arrival cost, which is a different thing, slightly difficult thing to do. You can use this also to have a very good training and sampling of learning-based approaches. So these are basically, and the last project was, or one of the last projects was OPC UA support, as we have mentioned. If you have a system that has connections with OPC server, as it could be in a more industrial setting where your sensors are just communicating through a server, and whenever they measure some information, they put it into the database in the server, and then your controller accesses that database, computes something, and then puts back the optimal controls on that database, and the communication between all different parts just takes place through this OPC server. Then we want to integrate these into MPC, and Alexandru Tetulea was already working on it, so there is a lot of results codes already there, but it's not completely ready. And that's basically it. Those are basically the plans that we had discussed for these days and that we would be working on. And of course, we are open if you are interested in something that you think it's important, either for you or for Do-mpc itself. You can just let us know, and we can also create a new project for it. So I think that's all from my side.
Yeah, thank you, Sergio. I would just quickly ask in the audience if there are any questions about the projects right now. The distribution, who's working on what, we're going to do after lunch. And then, of course, there's still time to discuss things. Okay, no questions? Then I guess we do the discussion afterwards. Then I just quickly, because it also doesn't take a lot of time, and then we have completed all of the online part as planned, I just quickly do the introduction to how we imagine our collaboration in Git during these days and also in the future, of course. So collaborative working with Git for Do-mpc. For this talk, I already assume that all of you have worked with Git before and have some basic knowledge. So the question is really just how are we using it for this project? And of course, we are not reinventing the wheel here, but I just want to let you know what our concept is. Yeah, basically the concept is as follows. There is a main repository for Do-mpc where Sergio and I and, for example, Benny are also the collaborators, and we can do changes to this repository. But as this project is growing, it is of course not feasible anymore to have everyone as a collaborator in this project. So what's going to happen is that we have main collaborators in the main repository, and everyone else we imagine to fork the repository and do pull requests to the main repository. This so far is quite standard. For this project work in the next couple of days, we are going to do a slight variation of that, in which all of the leads for the different projects, so each of the 5 projects that we have now defined, which we are going to work on, they are all going to have a lead. So Benjamin, for example, is probably going to be the lead for the approximation-based MPC project. So he's going to be the lead for this project. So what we are going to do is he is going to fork the Do-mpc repository for this project. And to this forked repository, he's going to add all of the collaborators which are working with him on this project. And somebody else might do a second project, and he or she is then forking the second project, okay? Yeah, everyone who is involved in a given project is then cloning the code, working on the code, and committing to their respective fork of the Do-mpc main repository. And yeah, that's essentially it. That's the first part. Then the second part is, how is this code coming back to the main repository and also back to the other forked repository? So getting back to the main repository is quite easy. Especially GitHub has this concept of pull requests for it. So if you have a fork and you made a change to your code, you can request to merge this change into the main repository. And then somebody who has admin rights to the main repository can review your changes and can accept them or reject them. Typically not reject them, but request some changes, of course. And the good thing is, because on the main repository, we are also running some unit tests, I can always see if these unit tests are passed with this proposed change. So I can see if somebody proposes some code breaking changes, and then I can easily, I don't need to clone anything, I can already see it in the GitHub interface, which is quite convenient. Yeah, and then if I have accepted the code, or Sergio has accepted the code, it is now in the main repository, but it also has to go back to the other projects, because maybe there are some important synergies. Benny is implementing a feature that is super important for project whatever, and then these projects have to merge their upstream changes into the forked repository regularly. Okay, so that's essentially it. You just merge back into your repository when there's a change in the main repository or in the upstream repository. Just a few pictures how this works in practice. Yeah, the project leads, they fork the Do-mpc repository. This should be quite easy for everyone. Then you add the collaborators. By the way, I'm distributing these slides as well, so you can have a look at this guide again if you need to. So yeah, you add the collaborators. Then you all clone the forked repository. You can use some GUI if you want to, but you don't need to. The following slides are going to be with the GitHub desktop GUI. So if you want to use that, then you can see how it looks like. I personally also use Git Kraken as an example, but if you're really professional, you just use the command line, of course. Yeah, this is how GitHub desktop GUI looks like. Here the first question is if you want to fork something to contribute to the parent project, which is here the case, so you just select that. Then you switch to the develop branch, because I ask all of you to always work on the develop branch. The main branch of the main repository is only for releases. So whenever we are changing something, we are doing it on the develop branch, and we are only merging the develop branch into the main branch if we want to draft a new release. If you forget about this part, it shouldn't be a major issue, but I still ask you to do it because it's easier and we don't need to fix any issues later on. Yeah, then you do your work, of course. So yeah, just change whatever you need to change. Use whatever IDE you want to. Here we are using Atom, which is my favorite IDE, but you can also use whatever you like, of course. You commit your changes to the code, which is hopefully self-explanatory if you have worked with Git before. Here I would ask all of you please to use very verbose commit messages. So really describe what you have been changing. I know a lot of us are using Git for their personal work. So the commit messages are often just update or change or a second change or whatever, you know. If you are working alone, this is fine. But if you're working in a team, we need some more explanation of what has been changed. If there's an issue on GitHub that you have been fixing with this commit message, please also refer to it with the hashtag and then the issue number, okay? Yeah, after a number of commits have been committed to the fork repositories, the project leads can create the pull request from this fork. This is super easy in this interface. You can also do it from the website of GitHub directly. In the pull request, please write again what has been changed in a nutshell. So yeah, again, just kind of summarize all of the commits that have been made to, for example, implement feature ABC, whatever, and give it a title that describes well what has been changed. I or Benny or Sergio will then review this pull request and accept it, hopefully, or maybe request some small changes. And then after something has been added to the main repository, you as the project leads should all get the newest version of the main repository, and you can do this by merging the upstream commit into your code. And for example, in this GitHub desktop GUI, this works like this. You just press on merge into current branch here in the settings. Then you choose the upstream develop branch, which is on the branch on which we are working on in the main repository. And then you get it back to your local repository and the work continues. Yeah, and that's essentially it. So this is the last slide of the presentation. And we are just slightly over time. So thank you very much for your patience. Are there any questions right now, or are you all hungry and just want to go for lunch?
We can also mention that we are open to suggestions for projects and for features from the audience also.
Yes, absolutely. So any project ideas, also for all of you who are in the Zoom call, if there's any feature you would like to see, we are always happy to hear what you would like to see in Do-mpc, and of course, yeah, from the audience as well. With the audience, we are later on discussing in more detail, of course, so that is quite easy to mention then what you would like to see additionally. One last thing, our main means of communication for this project is going to be the GitHub forum. So GitHub now has some discussion panel. So please use that if you want to contact us with new ideas or concepts or whatever, or anything you are interested in. And we typically reply rather fast. Not in the last couple of days because we were quite busy preparing this workshop, but generally speaking, we reply rather fast on this discussion panel. Okay.
Okay, so I guess this ends the live session.
This ends the
of
live
the
session.
First Do-mpc conference. So yeah, thank you very much, everybody, for joining, all those online and all those that are in presence here, of course. Yeah, but we'll see you later. And yeah, I don't know if you want to say the closing words, Felix.
Yeah, I'm not going to repeat your words. I think I'm just going to agree to them. So yeah, thank you very much. And yeah, hopefully we are going to have a couple of productive days.
Let's hope for it, yeah, for a long future of Do-mpc.
Yes.
So
and
thank you.
One more important part, which we can also do online. We have, of course, small presents prepared for all of the participants of the Do-mpc hackathon.
Only the physical participants.
Only the physical participants, unfortunately. So yeah, to our digital participants, we just extend our eternal gratitude. But to the physical participants, we have these amazing. Lucas, can we have the main camera, please? Yes. No, the other one. Yeah, this is great. Yeah, we have some amazing Do-mpc merchandise now, and yeah, we are very happy to give it away to our physical participants. It doesn't come as a big surprise because all of you have been selecting the t-shirt sizes. But yeah, regardless, for the sake of safety,
I think everybody can pick up.
Yes. So I would just ask you one by one to come forward and look in the box, which I'm putting here in a safe distance.
But I mean, we can do it also afterwards.
We can do it afterwards, maybe. Yeah, okay. That's a good point. Then I'm just quickly showing once more the beautiful t-shirts.
That are the ones that we are, of course, also wearing. Yeah.
Yeah, and thank you very much to our photographer. God, sorry, whose ever t-shirt this is. I'm not great in t-shirt folding. Should watch more Marie Kondo or something. All right, then that's it. Thank you again, and yeah, have a nice day.
Thank you, everybody. Goodbye.
Bye.